All right. Hey, everyone. For this walkthrough, I'm going to be going over the problem 2 on the exam prep week 12 worksheet. So this problem is called reverse engineering, and it's giving us basically these two arrays, right? An unsorted version and some version that's been um, sort of passed through some X number of iterations of selection sort, right? And so it's asking us, consider the following unsorted array, blah, blah, blah. Assume no two elements are equal. And then for each relation below, write greater than, less than, or question mark for insufficient information regarding the relation between the two objects. So what that kind of means is basically that we're trying to compare all of these objects. And pardon me if this is a little bit blurry. It's kind of a zoomed in picture. So we're sort of relating these two objects in each of these four pairs and trying to figure out if one of them, if we can say definitively that one of them is greater than the other, or that we don't have enough information to decide. Okay, so probably the best way to go about this is to first give a little bit of an explanation on selection sort. So if you're confident about selection sort and exactly how it works, feel free to skip ahead a few minutes in this video and just take a look at how I solved the problem. Otherwise, stick around for a few useful observations about selection sort and how we might break down this problem a little bit. Okay. So basically, the fundamental way that selection sort works is by considering our input list as two separate sort of portions. We have a sorted portion and an unsorted portion, okay? And at the start of our algorithm, the sorted portion is nothing, right? Which is why it's like kind of starting and ending at the very beginning of the list. It's empty. Whereas the unsorted portion is the whole list, right? And all we do in the algorithm is at every interval, we basically, sorry, at every iteration, we basically look for the minimum element inside of the unsorted portion of the list and swap that with the first element in the unsorted portion of the list. Okay, so let's try that on this down here. You can ignore this copy up here. This is the original list as well, but it's there for explanation purposes later. So we look through the entire unsorted portion of the list. We find that 0 is the minimum element, right? And then we basically swap that with the first element in the unsorted portion of the list. Okay, so we swap 0 and 2, and we get this. And now all we need to do to complete this first iteration of selection sort is to move our bounds around a little bit. Okay, so now no longer is the sorted portion just the or empty. The sorted portion is now going to be up to here. And meanwhile, the unsorted portion has shrunk by one element. It's now only 2, 1, 4, and 3. Okay. And then we just repeat the process. So now again, we look through this entire unsorted portion, find the minimum element, which in this case is 1, and then swap that with the first element of the unsorted portion, right? So once again, we swap 1 and 2, and then move our bounds one more time, right? Probably need to move this as well. So move like that, that, and this is going to be unsorted, right? And so you quickly see that we have a pattern emerging, right? We're sort of shifting this vertical bar right here, this guy. We're sort of shifting that with each iteration through selection sort, we're shifting that to the right by one element, right? Which means that we're sort of adding one more element to our sorted portion with each iteration. And so we're kind of building up the sorted list from the beginning all the way to the end. And you'll see that on the next iteration, since 2 is already in the right place, we sort of just move the bar immediately. And we say, okay, now we're here. And this is US for unsorted. And we kind of repeat the process until we're done, right? So for this problem specifically, the key observation to note about the way that selection sort is working here is that anytime we have a leftward movement, right, of an element, so anytime an element has moved leftward relative to its beginning spot, we know that that element is sorted. Now let me explain what I mean by that, okay? So if you look at our starting array up here, right, this is how our list started at the very beginning. 1 was at the the second index, right? The third position in the list. And now at this point in time, down here, 1 is now at the index 1, right? The second position, which means that it's moved leftward by 1 element. Similarly, 0 has also moved leftward by 1 element, right? It used to be here, and now it's here. So it kind of moved leftward by 1. And so what that tells us is that since 0 and 1 both moved leftward, they have to be sorted, right? At this point in selection sort, at this point down here, both 0 and 1 must be sorted, right? Because the way that selection sort works is that we're always taking the minimum element in the unsorted portion and moving it to the left, right? We're always sort of shifting sorted elements to the left of our list. And meanwhile, we're taking these unknown values and throwing them to the right? That's what happens whenever we swap the first and minimum elements, right? And so what that means is that we're guaranteed that if at any point in time we observe a leftward movement in our selection sort, we know that those elements are sorted. And sort of in comparison, a rightward movement doesn't really tell us anything, right? Because in this case, if we look at 2, right, 2 is a great example. So 2 moved right 2 spots, right, in this version of selection sort. But it just so happens that 2 is in the right place now, and so technically it's sorted. But if we move the algorithm 1 step back, right, let's say that we were 1 step before this, where our bound was here, and this was unsorted, 2 is still in the right place, right? 2 is sorted, and that's because we know what the elements are, so we can say that 2 is sorted. But selection sort hasn't actually gotten to the point where it's processed this 2 yet. And what that means is that we, because it was a rightward movement from compared to the start position, we don't really know if 2 is in a sorted position or not. And this is a little bit confusing because we know the numbers and we know what's going on. But these kinds of observations are going to be really useful up here, where we don't have any numbers to work with. We just have these symbols where we don't know what the actual values are, right? But the important thing to note is that leftward movements means that the elements are sorted. Rightward movements don't really tell us anything, and they're kind of ambiguous, okay? And I would take a moment, go ahead and pause this video, let that digest a little bit and sink in, because that's kind of the key for how we're going to solve this problem, okay? All right. So now let's take those observations and look at the actual problem. So at the start, we're trying to compare this. I'm going to call this symbol a pizza from now on, just to differentiate it, since we use it so much. So we're comparing this pizza to this circle, right? And we're trying to see if we, if we can do any of these, right? So let's take a look at our input list and compare it to at some, point after I iterations of selection sort. So we see that the circle is the very first element after I iterations of selection sort, right? And what that means is that since there's been at least 1 iteration and the circle is the very first element, we know that it has to be the smallest in the entire list, right? Because, if it's the first element and there's been at least 1 iteration of selection sort, then it had to have been the first thing we swapped in selection sort. And so since we know it's the smallest element, we can pretty easily say that the pizza is going to be greater than the circle, right? And, just as an aside, we also know that the circle moved left a ton, right? Which means that we know that it's been sorted, and therefore we know that it's smaller than the pizza. Okay. For this next one, we have the pizza again compared to, I don't know, this thing with 2 semicircles and a line going through it, right? So once again, we see that this guy actually moved right? So this shape ended up moving right by 5 spots compared to this, right? Compared to the sort of the place that we paused our algorithm, okay? But there's actually another key observation we should make here, which is that we know from the earlier, right, that the circle is the absolute smallest element in the entire list, right? And so when we swapped, we actually swapped it with this symbol that we're now looking at, right? We actually swapped it with this guy. So after 1 iteration of selection sort, let me do this. After 1 iteration of selection sort, this symbol should have been right here, right? It should have been in that position because we swapped it with a circle, and we kind of move forward. Since it's no longer right here, right, since it's now moved to the left one position, we see that, okay, actually, we can say that it moved to the left at some point along the way, right? We know for a fact that this symbol, this semicircle symbol with the line through it, has moved left at some point. Because if it didn't move left, it should have still been in this position, right? Because it would have been swapped with a circle and then never would have been touched again. And so the fact that it moved left means that we can use our case from down here, where leftward movements mean that elements have been sorted. And we can definitively say that the pizza is also greater than that symbol, right? Because it's moved left, excuse me, the symbol has moved left, whereas the pizza hasn't moved at all, right? It's in the exact same spot. So either the pizza is still unsorted or it's been sorted and it's greater than this symbol. But in either of those cases, we can say that it's greater than, okay? All right, let's see. So for the next one, this upside down triangle, we're once again comparing the pizza. So for this one, we see that the triangle has gone through an absolute sort of right movement, right? And since it's at the very end of our list down here, we know that it hasn't moved left ever since then. So it moved to the right when we swapped it with this infinity symbol, which is now the second element, and then it never moved left again. So what that tells us is that either both of these are unsorted, right? Since they haven't moved left at all, or they're sorted when they just so happen to be in the right place, right? But since we don't have enough information to say whether or not these two symbols are in the right places, we can't determine their relation, right? Because once again, we haven't observed a leftward movement for either of these two symbols. And so we have really no definitive information that either of them have been sorted. And so we can't say anything about their relation to each other. So this guy's going to be a question mark. And once again, I encourage you to sort of go back and digest that, because again, these are sort of some more maybe obscure observations of selection sort that take some time to really sink in. So it might be worth rewinding, looking at it, and then listening to that explanation again. Okay. And finally, we have no more pizza. We're considering the infinity symbol and its upside down triangle. Okay. So with the infinity symbol, we see that it's moved left a ton, right? Just like how the circle moved left from the very first step, we see that the infinity symbol moved left in assuming, or in apparently the second iteration of selection sort, right? And since it moved left, we know that it's been sorted, like we've dealt with it, it's been sorted. And we already know from the previous step, from the previous question up here, that this upside down triangle is either unsorted or it's the very greatest element in our list, right? And so in either of those cases, since the infinity symbol is the second smallest element in the list, it has to be less than this triangle, because either the triangle is the greatest element in the list, right, or it's been unsorted, in which case it has to be greater than the infinity symbol. Otherwise, we would have dealt with it before. And yeah, I think that's just about it. So the important kind of thing to note is that this left and right movement thing, it's a pretty useful observation about selection sort that might come in handy in multiple different applications. So just important to know that leftward movement always means that something's been sorted, whereas rightward movement means it's a little bit ambiguous. And yeah, I hope that helped. I'll see you guys next time.